All right, so here in Lecture 8, we're going to start working our way up to quantum mechanics and the electronic structure of the atom. This is Chapter 6 in that free online textbook. But first, we're going to talk a little bit about energy. Hopefully, this is just a review for you. Energy is one of those more difficult things to try and understand. The unit of energy is the joule. And you may recall from when we were talking about units that 1 joule is equal to 1 Newton meter. It's a force applied to an object over a distance. Okay. So whatever force it takes to move something across a distance is one way of thinking about energy. You can also think of it, as the effort you would have to expend to lift an object up a certain distance, a certain height, okay? Because in doing so, you put the force in to lift the object to overcome gravity, and you lift it up into the air, and suddenly it has potential energy. You let it go, and that potential turns into kinetic energy as it falls. So energy comes in a lot of different forms. Kinetic energy is the energy of motion. Okay? An object is in movement. When it's actually moving, it has kinetic energy. There's thermal energy, the energy of the random motion of the particles that make up an object. More thermal energy means it's hotter, it has a higher temperature. Gravitational potential energy is the energy due to the position of objects, in a gravitational field, You lift something up so it's further away from the other object, there will be more potential energy, more gravitational potential energy. You can have chemical potential energy, that's the energy stored in chemical bonds. So, say something like sugar has a lot of chemical potential energy stored inside of its bonds, but carbon dioxide and water, they are at the far end of burning something. That energy has already been released. So why doesn't water burn? It's already been burned. It's released all that chemical energy. Electrostatic potential, that's sort of like gravitational potential energy, only instead of talking about mass in a gravitational field, you're talking about charged objects in an electric field. Similarly, you can have magnetic objects in a magnetic field. They would have some form of magnetic potential energy. And also, finally, on this list, you could see elastic potential energy. That's when you twist or bend or stretch or squeeze an object. Okay, that'll change the physical structure. That'll stress the structure, and you're putting energy into the changed or stressed structure of that object. And that's elastic potential energy. Okay, so a rubber band, you stretch it, and you're storing energy within the warped shape of the rubber band. You let go, and that elastic potential is converted into kinetic energy, and the rubber band goes flying at your little sister. So, I meant to edit that out. The unit of energy is the joule. DWG stands for dead white guy. Once upon a time, I was amusing myself by keeping count of all the dead white guys whose names we collect. 1 joule is 1 Newton meter, and that's the energy necessary to move an object 1 meter. To lift, I should say, an object 1 meter. Now, hopefully that'll let you wrap your head a little bit around energy and what it is and how it can convert from one form to another. Let's start looking at the different experiments that led from classical physics, 19th century physics, balls flying through the air in arcs and electrical objects in electric field and things like that, to quantum mechanics, the confusing, fuzzy uncertainty thing, right? This is going to take a while. This is definitely more than one lecture to get through this set of slides. The first one we're going to look at is blackbody radiation. Okay? If you heat something up, it starts to glow. Okay? At a low temperature, like the temperatures you can achieve on your stove, it'll go a dull red. Okay? Then it'll go to cherry red, then eventually gold, then white, And if you were to keep on going, get hotter than the surface of the sun, it would eventually start to look like a very bright blue. And but we're talking about thousands and thousands of degrees. You don't want to do that. Don't try to get something white hot inside your house. The reason they call it blackbody radiation is because part of the work physicists were doing in trying to understand blackbody radiation was they said, okay, let's imagine an object that is perfectly black. It absorbs all light that touches it. And so in the exact same way, when you heat this object up and it starts to glow, it will glow perfectly. Okay, it won't be based on the chemical structure or the actual structure of the material or anything like that. It'll just be a perfect glowing object. Okay, so it's a black body, a black object. All right. Now the problem was that classical physics kept on running into a serious problem. Down here you see a chart, a graph that has wavelength of light on the x-axis down here, and then intensity on the y-axis. And then you have 4 lines. The red line shows the light emitted by an object at 3,000 Kelvin. Okay, and you see down at the very low wavelengths, there's like no light. Then the intensity starts to come up, and then it'll go back down. So it peaks right around here at a wavelength of looks like about 0.8.9 microns. And then the green line shows 4,000 Kelvin. All of the light is brighter and more intense, and the peak has shifted a little bit left to a shorter wavelength. And then 5,000 Kelvin, this is really hot, by the way. The peak has shifted even further to the left. It looks like we're at about 0.6 versus 0.7 versus 0.9, and it's really intense. Okay. This is just relative intensity, not any sort of absolute scale. This would be bright red or yellow. This would start looking yellow-white. 5,000 Kelvin would probably look white hot, maybe blue hot. Okay. So those are the actual lines that you can record if you look at something you've heated up. But classical theory, this over here, this black line, is what it came up with for 5,000 Kelvin. As you can see, it's not right. Not only is it not right, it's not even close. It is way the hell off. Okay? And they call it the ultraviolet catastrophe because over here, short wavelengths, this is going from redder or infrared microwave wavelengths going up toward red at around 900. Let's see. Oh, no, I'm thinking... No, that's right. At about 900, 0.9 is red. And then over here at 0.4, that would be blue. So the fact that it's okay-ish down here at the longest wavelengths, but it's getting worse and worse and worse as you get to shorter wavelengths, means you're going from red to blue, and so the ultraviolet catastrophe, because as soon as you get to ultraviolet, once you've gone beyond the visible spectrum, it's just complete garbage. And catastrophe just sounds cool. And they cared about cool in the 19th century, even though they didn't have a word for it. Okay. Now, the way physicists looked at light back in the 19th century was as a wave, like an ocean wave. And that's because of this thing over here on the right. Okay? They knew that light behaved like a wave because of this. Okay? So S1 means source 1, S2 means source 2, and F just means the final wall, wherever those waves hit. So if you have a source over here, and it's a wave that radiates outward, like blunk, you drop a stone in a pond, and it comes up here to a wall that has 2 slits cut in it, then the wave will propagate through both of those through each of those slits, I should say. So it'll radiate out from this one, and it'll radiate out from this one. Okay? So you'll have sort of 2 sets of waves coming and striking this wall. And if you record the way the water behaves at that wall, then these bright spots would be where the waves are going up and down a whole lot. And these black spots are where the water isn't moving at all. It's perfectly still. And that's because of what's known as interference. Okay? So where these two sets of waves overlap perfectly, okay, either line over line or space over space, that's called constructive interference. Okay, the peaks of the waves, the peak of this wavefront is adding to the peak of this wavefront. Where the blank spaces are overlapping, that's where the troughs, the valley, the low part of the wave are adding together. So that constructive interference, they're adding up. The waves are the peaks are higher, the troughs are lower, and that's the white spots. Where a line crosses a blank space, that's called destructive interference. The waves are canceling out. The peak of one wave is on top of the trough of another, and you get nothing. It goes to zero. Okay? Just to show you that, plus equals boom, just a flat line. Okay. So that's why you get this pattern here on the wall of intense wave activity and zero wave activity, is because of the overlapping these two separate wave fronts. Okay, you get that interference. This is what's known as an interference pattern. Okay, if you didn't have this second this wall with two slits in it, and then this final wall, if it was just the one source and then a place where you would measure it, you would just see water hitting the wall and acting like a wave. Okay, it wouldn't be a pattern like you see over here. This pattern is produced because you have these two sources of waves. Okay? And light does the exact same thing. And that's why they show it as this this pattern of black and white, because it's actual light making this particular pattern. Okay, the light is where the light shines, and black is where there's no light. Okay, so that's why they looked at light as a wave. It behaved, as far as they could tell, exactly like a wave, and so they analogized, light as if it were a wave. They said that it has a frequency. If you're looking at a certain point, the frequency is the number of peaks that pass by that point every second. And the wavelength of a wave is the distance between the peaks. Okay, so this is the wavelength, and that's the Greek letter lambda. It's traditionally used by It's traditionally used by physicists to talk about wavelength. Whereas frequency, we use the Greek letter nu to talk about frequency. So, and the units, the units of frequency are per second, 1/seconds, or hertz. And the units for wavelength are just distance, so meters, microns, nanometers, and so on. So a wave has a frequency, a wave has a wavelength, and a wave has an amplitude. That's the height of an ocean wave or the intensity of your light. So you could have something that's low amplitude or something that's very high amplitude. And finally, you have speed. Okay, the speed of your wave as it travels through the medium. For ocean waves, the medium is the ocean, and then the wave is what's traveling through the ocean. The water actually stays put. The ocean wave passes through, the water goes up, the water goes down, the water ends up right back where it was. The wave, the energy, is what's traveling through the water. The water itself is not actually going anywhere. And a thing to note, the speed of a wave is equal to the frequency of the wave. It's not actually V, it's kind of swoopy. The frequency of the wave times the wavelength. Okay, so you have meters times 1/second equals meters per second. Okay, so that tells you how quickly the energy is moving through the medium. So a sound wave moves at roughly 300-ish meters per second, I think. I don't have that fact on hand, and I ain't going to Google it. Oh, well, that's 15 minutes. Let me just go ahead and finish this slide really quick. All right. So, and just as the taller an ocean wave is, the more energy it has, okay, because it takes a lot more energy to lift water up a very big distance, okay, we're talking potential energy there, than it does to lift water up a small distance, okay? So an ocean wave, the energy of the wave is measured by the amplitude, okay? So the intensity of light tells you about the energy of that light, okay? As you reason by analogy to an ocean wave. And that makes a lot of sense. You put your hand close to a dim light bulb, it's going to feel warm. You put your hand next to a bright light bulb, it's going to feel very warm. If you were to actually touch the light bulb, it would probably be so hot that it burns you. I recommend you don't do that. Okay. And finally, and as I said, wavelength times frequency is speed, and that tells you more about the physical property of the medium itself. Sound travels at different speeds in different mediums, or media, because they're made of different materials. So sound travels a lot faster in water than it does in air, and it travels even faster in something solid like a steel bar or something. Okay. And according to classical physics, that is irrelevant to energy. Okay. Now, in Lecture 9, we will go on and start talking about a German named Max Planck and his work to try and solve blackbody radiation.